So in this particular problem, we're trying to solve for the velocity time equation given this graph. It's a graph of velocity versus time of a mass undergoing simple harmonic motion. So to solve for the velocity versus time, we've got to go to the equations that we have derived. So on the AP test, you're probably better off deriving these equations. You can write them out directly if you have them memorized or if you have them in your equation sheet. So we know that the velocity function for an object undergoing simple harmonic motion without any dampening is this. Dampening is a college level topic, so don't worry about that. In AP Physics C, the equation is minus a omega sine omega t, where a is the amplitude. And we also know that the coefficient in front of the sine, minus a omega, is equal to minus v max, where obviously v max is going to equal a times omega. So to figure out v max in this particular problems, it's relatively easy. They give us the graph of velocity over time, and we can look at the maximum velocity, and it looks like it's right around 0.16 meters per second. 0.16 meters per second. So we're going to have to estimate a little bit, but that's a good enough estimation for our purposes. So when we go back to the equation, we're going to enter in 0.16 meters per second for the maximum velocity. And again, we're getting that from the graph. So let's just enter our value in here of 0.16 meters per second into this equation. Again, we get that from the graph. So let's go ahead and write out this equation. But first we've also got to figure out what omega is. So we know from our equations that omega is the angular velocity, and the angular velocity is 2 pi radians divided by the period. All right, 2 pi radians divided by the period. Sometimes you'll also hear this as the angular frequency. So 2 pi radians over the period. And the period we're going to have to find by going back to the graph. So remember, make sure you measure the period as the time it takes to go from one amplitude to the other, okay, or one crest to the next crest, or one trough to the next trough. So in looking at that graph, it looks like the period is right around 0.7 seconds. Okay, so again, the graph, if you go from crest to crest, is about 0.7 seconds. So that gives us an angular velocity of right about, so our angular velocity is right about 9.0 radians per second. So now that we've got the angular velocity, we can plug that back into our original equation and write out our complete equation now that we've got V max. So the velocity as a function of t is going to be 0.16 meters per second, because that's our maximum velocity, sine omega t, but for omega we're going to put in what we just calculated as 9 radians per second, times t, and remember that the units just go in the coefficient before sign. The other part's unitless. So the second part of this question asks us to find the position function. And to find the position function, we're going to have to use our XVA mnemonic. Remember, our XVA mnemonic tells us in what direction we're going to take the slope and in what direction we're going to take the area. But because this is AP Physics C, we're going to use derivatives and integrals. So that's right, we love Miss McCullough. She does half my job for me. I love you, Miss McCullough. Okay, so let's write out our XVA mnemonic. Okay, previous self, write down XVA mnemonic. Hurry up, I only want to do this once. Okay, here we go. XVA mnemonic. In that direction, we're going to take the derivative. In the other direction, we're going to integrate or take the antiderivative. Excellent. So as we integrate to find our position function, we want to integrate to go from velocity to position again. So we're going to take the integral here of the velocity with respect to time. So we're integrating v dt, where we already know our function for v. As being 0.16 meters per second times the, I'm sorry, that's actually 0.16 meters per second. And the sine of 9 times t dt. So as we integrate this, remember we would take the coefficient in front of the t, or the constant in front of the t, and that goes in the denominator. The coefficient or constant in front of the integral remains negative 0.16, and when we integrate, we get a negative of cosine times 9 times t. So just like I said just a second ago, the constant, negative 0.16, has to go in front of the that set of parentheses there. So as we integrate this, oh, okay, yeah, that's right. We have to write out the constant of integration. All right, and then multiply out our constants so that we get the right value. So we can figure out our constant of integration now by substituting 0 in for t. So as we do that, if we just plug back into the equation above, it'd be negative 0.16, but the negatives cancel with the other negatives, so it's just 0.16. Cosine 9 times 0, because we're entering in 0, divided by 9. Okay. And we know that that will equal, what will that equal? That will equal, I think it's what, 0.18? Okay, that will equal, oops, 0.618, 0.018, I guess. And that'll be in meters. And so we just plug that back into our other equation, our previous equation, to get our position function.